Hello class, this is a tutorial on understanding tree diagrams. This is the same experiment as the previous one I showed for the two-way tables. Okay, and however, this is just a different way to represent all the possible outcomes using a tree diagram. So I want you to think of, well, the way I think of it is, let's say in the first bag, let's say bag with numbers. Well, with a bag of numbers, numbered tokens I mean, there are a few things that can happen. You can get a 1, you could get a 2, or you could get a 3. And let's think of it this way. Let's say just as you're about to take a token out of this bag, 3 things can happen, can't they? Alright, so that's why we draw one path to each of them. And then after this we have the bag of colors. So now let's say we're at, let's pretend we took a 1. After we take a 1, what things could happen? Well, after we take a 1, what could happen is we could get a red. Okay. Well, after we take a 1, we could have also gotten a blue. But after we've taken it, we could have also gotten a green, or we could have also gotten a yellow. And then can you see how this same thing could happen with this branch of 2? After we take the 2, we could have gotten a red, we could have gotten a blue, or we could have gotten a green, or we could have gotten a red. Oh, sorry, yellow. Not red again. And the exact same thing can happen for the 3. We could have gotten a red, could have gotten a blue, or a green, finally a yellow. So this result here is a 1 red, 1 red. This one here is a 1 blue. This one's a 1 green or 1 yellow. This one could be a 2 red. This one could be 2 blue, 2 green. This one could be a 2 yellow. This one could be a 3 red, 3 blue, 3 green, 3 yellow. Can you see, if we were to compare it to the previous video, there are also 12 in total here. There are 12 total outcomes. And we get that by doing 3 here times 4, because there are 4 for each of these branches, because here's what of set 4. That's 4 for that one. That's another set of 4. Another set of 4 for this one. Another set of 4 for this one. Which gives us 12 total outcomes. And the same thing can happen now. You can be asked questions regarding, so if I ask you, what is the probability of getting a 3 and a red? Well, how many results here have a 3 on them? 1, 2, 3, 4. So for 3, there could be 4. You can get a 3 red, 3 blue, 3 green, or a 3 yellow. But with the red, well, there's going to be there could be a 1 red, a 2 red, or a 3 red. But we don't want this. We want 3 and an R. Now remember, if you go back to the Venn diagram, it's as if we're overlapping. So are there any results here that overlap in both groups? Well, I hope you can see it. There's one here. That gives us only one. There's only one overlap out of the 12. But that is what's known as a basic tree diagram. So let's take now, for example, this following probability experiment. Okay, let's say that I'm playing a game, and no, let's say not me. Let's say Bob is playing against Charlie. Alright, playing against Charlie, 2 rounds of a game. Make it a very ambiguous game. And in this one, Charlie is much better than Bob. So Bob's chance of winning the first round he's got a smaller chance. Let's say he only has small chance of winning the first round of 1 in 4. He's got a 1 in 4 chance of winning the first round. Okay. If Bob wins the first round, his chance of winning, sorry, not chance, his probability of winning the second round increases to 3 out of 5. So let's first represent what this might look like, okay, in a tree diagram. Well, if we look at this first, let's say let's label this as first round. Well, in the first round, it says 1 in 4 chance of winning, or 1 in 4 probability of winning. Does that mean there are 4 paths? If we were to think about that conceptually, it would be 1 path leading to victory and the rest leading to losing. 1 in 4. But if we were to do this, okay, as a tree diagram, you get crazy big. So instead we create what's known as conditional tree diagrams. Give it a little label here. These are called conditional tree diagrams. Conditional tree diagrams. Where rather than representing it physically as 1 in 4, like I showed, 1 chance of winning in 4, instead, well, let's think of it this way. Bob can either, in the first round, win or lose, correct? Let's just draw this for now. And instead of drawing 3 more branches that have loss, let's say that the chance of him winning will write the probability along the along the branch. So his chances of winning is 1 in 4. Well, if he has a 1 in 4 chance of winning, it must mean he has a 3 in 4 chance of losing. Okay. Now, in the second round, it says that if Bob wins the first round, his probability of winning the second round increases to 3/5. Well, let's just pretend that Bob did win. So he went down this path. Again, on the second round, he could either only win or he could only lose. But now, instead of it being the same as 1/4, his chances of winning, okay, has increased to 3/5. And again, if we were to do this conceptually, there would actually be more branches. This one here is a win. This one here is a win, which gives us 3 branches of winning and 2 branches of losing. So it's 3 wins out of 2 losses. But again, that would look far too large and too messy. So instead we create this, a conditional tree diagram. So again, if that was 3/5, this one here must be 2/5. And if he loses, however, it doesn't state what would happen. Let's just assume that it stays the same. He could either win or lose, but his probability stays the same. So his probability of winning is 1/4, and his probability of losing this one is 3. Is 3. Not 3. I was about to write 3/5. 3 out of 4. So in this one here now, his chances of getting a win and then a win. So a win-win, WW. Okay. The probability of this happening is actually the product of the branches that it took to get there. So it would be 1/4 times 3/5. I'm going to write that underneath here. So in the first one, for him to win, he's going to get 1/4 times 3/5. That would give a result of 1 times 3 is 3. 4 times 5 is 20. So his probability of getting a win and then a loss, so a WL, same thing. We multiply the branches it took to get to this endpoint. So it'd be 1 out of 4 times 2 out of 5. And that gives us a total, well, 1/4 times 2/5. It's 1 times 2. That's 2 out of 20. Normally we would simplify this, but I keep it the same just so that you can see that these denominators for all of them, I try to keep all the same. So this path, it's a lose and then a win. So what's the probability of him getting a lose and then a win? So a L then W, well, it's a 3 out of 4 times, that's 3 out of 4, that path, times a 1 in 4. So 1 in 4. That gives us 3 times 1 is 3, and a 4 times 4 is 16. This one here would be a loss and then a loss. Okay, 3 out of 4 times 3 out of 4. 3 out of 4 times 3 out of 4. That gives a 3 times 3 is 9. 4 times 4 is 16. A 9 out of 16 chance. So from this point on, it's a lot easier to calculate probabilities of this result. So let's say they ask us, what's the probability of Bob winning the game? Well, in order for him to win the game, right, he needs to win both rounds. But we've already calculated that. It's 3 out of 20. So it's the same as probability of getting a win, which is 3 in 20. Well, what would the probability of losing the game be? Losing the game be? Well, that's the same as getting a probability of getting a loss and then a loss. We've calculated that as well. We already have it here. It's 9 out of 16. And then what would the probability of getting a draw be? And then in this game, the draw is if one wins and the other loses. Well, there are two ways in which we can get a win and a loss. Win-loss or a loss-win. Okay, so what we do for this one, it'd be the sum, the probability of a win-loss plus the probability of getting a loss and then a win, which would give us, well, probability of a win-loss is here, 2 in 20. 2 in 20 plus the probability of getting a loss and then a win is 3 in 16. Adding these together, we would get, normally I would do this by hand to get the same base or the same denominator. Well, I'm just going to rush it. It's going to be 2 in 20 plus 3 in 16. There's a 23 in 80. A 23 in 80 chance it's going to be a draw. So if we do that as a probability, as a percentage, sorry, that is the same as a 28.75% chance of a draw. That concludes conditional tree diagrams.